Thanks for the invitation. So the problem I'm going to talk about is basically a scattering theory for a nonlinear Klein-Gordon equation in one dimension in the case where there is long-range scattering involved in the nonlinear sense. And this problem is motivated by the problem of studying the dynamics of kinks, large time asymptotic stability of kinks, if true. So this is what I'm going to talk about is a joint work with Hans Lindblad and Igor Rodnianski and Jacob Sterbenz. Okay, so if you take the nonlinear Klein-Gordon equation, say, then there are solutions which are kink type solutions. In other words, solutions which are equal to a constant at plus and minus infinity, which are smooth, and such that the constant is different at plus and minus infinity. And we are now in one dimension. In one dimension, and u here is a function of x and t. So there is a solution which I will call it kink of x and t. And in some cases, sorry? Yeah. Okay. So so k is so k in some cases is known. For example, when f of u is in what is called the Klein-Gordon equation, then we know how to solve this problem. And in the phi to the 4, there is also possible to write down explicitly the kink. But in general, there will be a kink solution also if you take small perturbation of the known examples. And our analysis of the linearization of this equation around the kink solution, let's say in these two cases, the phi to the 4 theory and the Klein-Gordon, showed that there are some fundamental difficulties in trying to understand the dynamics of this problem as opposed to the soliton plus perturbation. The reason is that the linear problem is already very difficult in this case because there is zero energy resonance in some cases to the linear operator. And when you linearize this equation, you get a linear part plus a nonlinear part. So the linear part is a linear operator which seems to have zero energy resonance in some cases, which means that the decay rate in time of the solution in L infinity will be t to the minus half, and not better than that. So just like the free Laplacian in one dimension. So because of that,
the kink solution, the kink solutions I know don't depend upon time.
no, but you linearize. You linearize the equation around kink.
Your equation probably has a Poincare symmetry.
What?
Your equation is a Poincare invariance the way it is written.
Yes, it is Poincare invariant, and the t is because it moves. It moves. It moves. That's why. So you let's say that you.
I mean, it's presumably to the orbit or something that doesn't.
Yes. So let's say that you freeze it and you get a function k of x, and you linearize around this function k of x, and we can just write down simply the equation, and then you will see that when you plug u as k plus perturbation, right? Then the equation for u tilde contains linear terms and nonlinear terms, and the linear terms will be powers of k times u tilde, and the nonlinear terms will be again powers of k times u tilde squared, and nonlinear terms, and so on and so forth. So then the question arises, before you can actually solve the problem, is first of all to understand the equation for u tilde. So what is the equation for u tilde? So you will get an equation, and now I will take the simplest thing that I can think of for u tilde, which is this one. And now I just replace u tilde by u. And then I have now a linear term. Now, I'm not going to solve the problem with linear term. I don't know how to do it, and you will see later why. But I want to solve the nonlinear problem. So the nonlinear problem in general will have alpha of x times u squared plus g of x times u cubed, let's say. And these are the problematic terms. There is higher order terms, but we don't have to worry about them because they are. Yes, from now on, u tilde is u. OK, so now the problem that I'm going to discuss today is dt squared minus Laplacian u plus some constant. Let me just fix the notation once and for all. So I will take some constant for the u squared. Let's call it alpha 0 u squared. And then I will take some beta 0 times u cubed plus g of x u cubed, where now I will take g of x to be nice, smooth function. So g of x is going to be, say, c0 infinity for simplicity. And
does it have compact support?
yes, compact support. I mean, it's not used that it has compact support. What is used is that g of x dx, g of x dx is equal to 0. If it is not 0, you can add a constant to here. But even that, I'm cheating here a little bit because the problem, the original problem, actually may have g of x. The original g of x in the original problem may have different constant at plus and minus infinity. So you cannot always arrange this. But let's say I arrange that. Yes, the derivative doesn't have compact support. It will be exponentially decaying, let's say. But so if I can subtract a constant term, I will put it here. So I'm looking at a simplified problem where
We don't have to know what the kink is.
yes, you don't have to know what the kink is. I would like to explain how to solve this equation, if possible.
And you drop the linear term.
And I drop the linear term, and you will see in a moment why I dropped it.
Because you can't do anything with it.
I cannot do anything.
But if I have a pure linear term, then you could do that, right?
Yes, but even in that case, there is a resonance in certain cases. So the problem is not trivial. You get e to the minus half in any case. Yeah.
I'm a little disturbed by the power of u cubed.
Why?
Well, because normally you would like to have a stable equation, for example, f of u equals u cubed. And then you linearize about the solid part, then I guess
You don't have this term in that case.
the
Yes.
maximal nonlinearity would be a u squared.
That's right. That's right. You have to take higher order. You're absolutely right. You have to take higher order before you begin to see a u cubed term like that. You make small perturbation like u to the 4, u to the 5.
The u squared would already be interesting.
We don't know how to do the u squared term with non-constant coefficient. It's too difficult at the moment. But the methods that I will describe actually shows what to do also in the case when u squared. So alpha 0 is taken to be constant here. Otherwise, the problem is much harder. OK? That's the situation today.
So if I say g is 0,
Yes?
then what do we know about this?
OK, I will say a few words about that. Yeah. So
The whole point will be what the region of g is.
yes, the whole problem is what to do when g of x is not 0. That's all. So what is known about this? So first of all, in the free case, one can write the asymptotic solution of this problem in the following form. You can write that u of t and x behaves like rho to the minus half. I will define it in a moment. E to some phase, phi of rho and say x over rho. A of x over rho plus complex conjugate in some sense, rho e to the minus I phi sem phi a conjugate. This is in the free case when
Alpha, beta, G of equals 0.
yes, and here a, in fact, a of x rho is known explicitly in this case. It is given by the square root of 1 plus x squared over rho squared times the Fourier transform of minus x over rho. So this is, one part of the solution. And let me just define here x to be rho sine hyperbole of y. And I will define x to be rho sine hyperbole of y and t to be rho cos hyperbole of y. So these are the hyperbolic coordinates, which I'm going to use from now on. I'm going to use rho and y later. Okay. So this is the asymptotic behavior of the solution of the free problem in one dimension. So the question is, what happens when you take alpha 0 u squared and beta 0 u cubed added to this equation? Then this becomes much, much harder problem. And the asymptotic behavior is not given by the free solution anymore. And the reason is that if you plug in this kind of an expansion in here and in here, you see that this acts like a time-dependent potential, which decays like t to the minus half or rho to the minus half. And this decays like rho to the minus 1. These functions are not integrable, and therefore they contribute something non-trivial to the asymptotic behavior. So in order to solve this problem,
Now, I have two more questions.
yes.
So you have an amplitude which...
Amplitude and phase. And rho to the minus half, factor out.
What is this phi, though? Did you tell us what the phi is or not?
Phi. Phi is
Maybe we don't need to know, but
no. I will tell you what is phi in the case where you add these two terms, because then it's interesting. Otherwise, it's nice and smooth function. It's bounded nice and smooth function. So I will tell you what it is in the general.
I probably need to know things about derivatives and where it has stationary phases and things like that.
Yes. So it's a nice function in when there is no such terms. And it turns out, and this is what one can show, is that it becomes a badly behaved function once you introduce these terms. But it's actually, one can construct it explicitly to any order. So that's what I will show you.
Okay, but now I'm still a little bit confused. What is your initial data here, and how does it appear, or doesn't it matter?
No, we want to do life as simple as possible. Initial data is C0 infinity.
But that's fine, but
Oh, that's the U hat.
U hat is the Fourier transform of the initial data.
Oh, okay. So that's the first thing.
Yes? Yes.
But you only have the initial, so at time 0, it's 0, and then I have a derivative at time.
Everything, it's the simplest possible problem on Earth. C0 infinity initial data.
but then everything for the free problem, everything propagates along the light cone.
Yes.
So I'm not sure what.
Yes, this is, here is the light cone. This is singularity. What is rho? Rho is x squared minus t squared square root. Right? So that's where the singularity is, on the light cone. That's how the solution looks like.
Yeah, I'm not used to seeing it in that form. I guess yours is
Yes, I
light cone, that's the
I
light
know
cone.
you have to get used to it. Light cone is rho equals 0. Okay, so yes, what?
There's no singularity on the light cone.
What do you mean no singularity on the light cone?
Should you make the drawing? Maybe we should make a little drawing. All the xt plane.
This is the asymptotic behavior. What's singularity? There's no singularity.
You're looking at large.
Yeah, large rho. Yeah.
Large
You
times
just
large
said that
Yeah.
on the light cone there is a singularity.
Well, I said yes. The singular rho to the minus half is singular on the light cone, but this is not an expansion near 0. This is expansion for large rho. Okay. The asymptotic behavior.
Go into the interior.
Yeah, the interior is much is
There it's zero normally
yes.
because of height.
Right. Well, why are you confused? There is extra constants here. Well, no, you're thinking about the wave equation. You're thinking about the wave equation, but the Klein-Gordon equation does not have the Huygens principle. There is everything.
No linear term, it's not Klein-Gordon. It is the wave equation.
Yeah, you're missing a linear term for Klein-Gordon. Then I understand better.
Sorry.
You're missing a linear term.
Yes. Where is it?
Well, I can tell you what it is if you want to know.
Mm,
Minus Laplacian plus 1.
plus u, yes, plus 1. Yeah.
Now we're happy.
Okay.
Okay, now,
Yeah, otherwise you could write them down and you just have it.
now, so now the question is what happens when you add these two terms, forget about this one. Then the first result on this problem was done by the law.
You have a linear term, but it's just not spatially dependent.
Yes. So now we add these two terms, and this problem is much, much harder to solve. It's not true anymore that asymptotic behavior is free. So you have to do normal form transformation to eliminate the u squared term, and I will explain in detail how this is done. And you also later have to do normal form transformation to eliminate the u cubed term, because this is how it originally it was done, because it contributed something which is logarithmically divergent. So you cannot just estimate in a simple way the equation. And after you do all these things, miraculously, you can actually compute exactly the leading behavior like that for this problem. And this was done by the law. Okay, so what he got.
So the classical people are much behind the quantum.
Why is that?
This is just a 5 to the 4th in 1 plus 1 dimension. And
Okay. Okay.
did all these cluster expansions for this problem.
Okay. So I will write down the result, and you tell me how you get it from cluster expansion. Okay. You non-standard analysis. I don't care. I just write the result, and you'll tell me how to get it.
It's going to be quite different.
Okay. So here is phi 0, the phase. Rho. It is rho plus 3 over 8 beta 0 plus 5 over 12 alpha 0 squared a of x over rho squared log rho.
What is this?
This is the phase when you add the nonlinear terms.
The nonlinear problem.
Yes. The leading order of behavior.
So your u is not real.
No, it's real because there is it's this plus its complete conjugate. Yeah, it's real. Yes. So now that's what you get. That's the leading behavior, and this is the singular behavior part. Everything else is kind of nicer. Now
What sense is it nicer? Do you have higher powers of
it's nicer in the sense that you have higher powers. I mean, I got the expansion. So the law did this by he did this by brute force normal form transformation. So which is used to eliminate this term and this term, and it is based on the method that originally Chata developed. Okay?
When did you do this?
Huh?
When was this done?
I think early 90s. I don't remember. Something like that. Early 90s. Okay, then Lindblad and I worked on this problem again without this term, only this term, as well as for the nonlinear Schrödinger equation, which is equivalent to this problem in one dimension. And we got the same result. And we didn't have this term because we didn't put the u squared term. So we got the same result, but we also got the asymptotic expansion. So in other words, we got a machinery, a system of an ODE that if you can solve it iteratively, you can get this function and the next terms. And they all look like smooth functions of x over rho, which are polynomially decaying times powers of log rho. So this is how the expansion looks like. The expansion is in powers of log rho times a symbol which is nice of x over rho.
But the next terms are higher powers of log? Or
Yes, yes, higher power. Yes, higher power.
But then in what sense are they smaller?
Well, I don't know if it's smaller or higher. It is good in the sense that these guys, you get better, a symbol which decays faster and faster. That's what we get. So our expansion is for the A and for the, I don't know if in what sense it is better. In the following sense, I can tell you that it is better, is that after you subtract the first n terms that we have in the expansion, then the leftover decays like t to the minus capital N over 2. So the expansion is better in the sense that the solution decays faster and faster in time. So in other words, here you will have better and better factors. Okay? Yes?
What's the regime in which you want to understand the solution? X over rho is apparently the same as the hyperbolic sine of y.
Yes.
So it could be very big. What's big, what's small in your expansion?
Well,
I don't understand.
this problem has difficulties at frequency near 0, but I'm interested in the behavior for large rho.
But this x over rho is what kept constant for one.
What? X over rho. X over rho is y, right?
This singe y.
Yeah. Yes, which is so y. So
Because in your
yeah.
formula,
So y near 0 is another difficult region, which we have to understand. But look, you have to construct the solution everywhere because you want to prove global existence. So the problematic regions are what happens when rho goes to infinity and y near 0 as far as derivatives with respect to y are concerned.
And the A, when you have asymptotic?
Yes. Yes. Okay, so the theorem that we can prove in this case is that for initial condition which is compactly supported and with this function smooth and rapidly decaying, then u of t of x has global solution here u of 0x is C0 infinity. So then you have global solution, and furthermore, u of x and t is bounded by some constant which depends on the initial data.
Is a global solution. And the solution cannot get the solution. What's the state?
Yeah. So let me. Equation 4. Yeah, with the G. And here, what I'm assuming is that G is rapidly decaying and smooth.
So you're saying, what is that thing? What was it, a half down there?
Yes, 1/2. You cannot do better than that. Yes, 1/2. Yeah. Yes, so that's 1/2. Okay.
And then, so that's the statement, or?
Yes, that's the statement. We didn't do asymptotic expansion in this case for the iteration.
So your statement is that the soup norm continues to decay as if it were free.
Yes. Yes. In fact, we control other norms, but you will see later that we have to control other norms in order to get this. This is a consequence. But in order to prove it, we control other norms.
Talk about the phases.
What? No. We control other norms, you'll see. OK, so the first step in the analysis of this problem is to rewrite it after doing some changes of variables and rewriting it differently. First of all, I do the change of coordinates to y and rho, and then I pull out rho to the minus half from u.
Can I ask you another question?
Yes.
So this is all small data state?
Yes, small data. Small data. The only thing which is not small data in this kind of a problem is a result of Lindblad and mine, which shows that if you take asymptotic state to this problem of the type which has the right phase, then we can construct initial data which corresponds to that.
So you're sort of
So we can only prove, yes, we can prove existence of evaporators for large data, but not completeness. Okay, so now in order to analyze this problem, we actually do not analyze the equation for u. We analyze the equation for v, where v is defined as rho to the minus half v is u. That's the definition of v. And now I will write the equation for v, which is what we are going to analyze. And the equation for v will look like d rho squared minus 1 over rho squared dy squared plus 1 over 4 rho squared v equal to alpha 0 over rho to the 1/2 v squared plus beta 0 over rho v cube plus some beta tilde of rho y over rho v cube. Dimension 1. So the fundamental problem will be this term, even though this is rapidly decaying, and I will explain why. So you have here a linear problem, which is kind of nice.
oh, I see, there's the y. Okay.
This is the one.
Coordinates, right?
Yeah, this.
You're in a row y coordinate.
So this is the one which I missed before, but okay. So now, as you can see, the v squared is a disastrous term because you have 1 over square root of rho, which is just, you cannot control it by integrability or whatever. Usually, how do you would like to write an energy estimate. So the method that we have for getting a priori estimates on this equation is to write down of some kind of fancy energy identities, energy estimates. So we write down an energy functional, and we show that it is bounded, except that this term will always contribute a term which is the integral over rho of this term in the corresponding norm. The problem is that this is not integrable, and this is logarithmically divergent, even if you know that v is bounded. Let's say that you know how to prove that v is bounded. Then you still have here too much divergence, and so is here. And this one, of course, there is also divergence, but the question is what to do about that. So now, what is the idea of normal form transformation? How do you attack this problem? So the way this problem is, yes?
I guess I'm correct. The V has now essentially no decay in rho.
Exactly. You want to prove that v is in L infinity and small.
Okay.
You start with v, which is small and smooth and compactly supported, and you want to show that it stays small for all times. That's all.
And in other words, in spite of the fact that all the nonlinear terms have an inverse power of rho, it doesn't mean that they become insignificant.
That's the problem. The term which has higher powers of rho will become insignificant, but this one are not because when you do the energy estimate for this kind of an equation, the contribution of this term will be the integral over rho of these quantities. That's the problem. That's where the problem comes from. Okay. So what is the way of attacking this kind of a problem? This is, you do it by normal form transformation. So the idea is that you write v as omega 0 plus omega 1, and you write omega 0 as the solution of the free problem, and then you write omega 1 you write as a solution of an equation which exactly cancels the bad guy. So you try to construct omega 1 so that it exactly cancels the bad guy to leading order. You never construct a solution which exactly cancels the bad guy. It cancels it to leading order. That's the idea. So then you need to have some kind of an ansatz. How should this W1 look like? Plug it into the equation, and then arrange the ansatz so that it will cancel the leading order term. This is the way Chatat did it, for example. Okay?
So that's it. It's just a linear. It's not multiplicative. You're writing it linear. You're writing it additive. You're writing.
It's yes. It's this. No. The cancellation is of course additive, but omega 1 is not linear. So omega 1. Now I need an ansatz for omega 1. So omega 1 will be 1 over rho to the 1/2 times a bilinear operator in U and in V, in V plus 1 over rho to the 1/2 some other K1 and K2 of V dot. And so now, yeah.
Omega naught is a constant?
No. Omega naught solves the free equation. Right?
You want this, let's see. You want the V to be constant, right? You like it to be constant.
What?
The V.
The V I want it to be
constant.
not constant, uniformly bounded by something small.
Okay.
Yeah. Yes.
I mean, suppose to do a somewhat simpler problem that we put g of x to 0.
Yes.
to start with.
Yes.
Then, I mean, the normal form is very easy. You just translate, you write down the energy function for your equation.
Yes.
You translate to a local minimum of the energy function, and then expand that out there. Right?
I don't know. I mean, I don't know how to.
I think it's more sophisticated.
I don't know how you can get it this way. I mean, I can tell you that.
I mean, you know, this is a phi 4 plus phi cube.
Yes.
Really,
Yes.
So we write all the potential. It has a local minimum somewhere and then an absolute minimum. I can look at small sort of solutions that are small fluctuations about the local or the absolute minimum.
Yes.
Is this not what you're doing?
No. No. I don't know if it is more sophisticated or less sophisticated, because this way of doing it is something that Hugh doesn't like. He calls it trial and error. And this is trial and error. You just try a quadratic. You just try a quadratic functional, and you plug it into the equation, and you derive equations for K1 and K2, and you construct them explicitly. This is what Chatat did. This is what Delors did. That's what everybody did. What? No, one dimension. One dimension. So now you take this assumption, and you ask yourself, let's call this operator L0 for a moment. So you ask yourself, how is it possible to solve L0 omega 1 equal to minus alpha 0 over rho to the 1/2, say, V squared, equal to something which is nice. And nice means higher order. For example, it is 1 over rho. So this has to be 1 over rho.
Yeah.
Okay? So that's the idea. So now you do the computation. For K1, you write down, you just plug in these two creatures into the equation and you just compute this equation.
So are you really looking at the lower equation, or is that just a sort of?
I'm just now telling you a simplified problem, how to knock off this term if I was just doing what Delors did.
Yeah.
Okay? Because that's the starting point.
Sure.
What?
I'm still confused by many aspects. For example, I don't know what you mean by small data. You see, if you said small oscillations about a minimum of the energy functional, then I would know what you mean. But small data doesn't mean anything interesting if you have a U squared term.
Okay, you will see in a moment what is small data. Small data will be small in the norms in which I close the bootstrap equations.
But they will not remain small. That's what I claim. You can start
Certain norms remain small for all times. Okay, we will see.
Should I tell you why?
Please, go ahead.
Why don't you draw the potential of your energy function?
Yes,
There's a new cube term and new fourth term.
yes,
Let's suppose I look at the solution that doesn't depend on x at all.
yes,
Just on time.
yes,
Do that.
yes.
Then if I start with small u, it will roll down and oscillate like hell
I know,
around
I know. Part of the solution is constructed by solving the ODE, which corresponds to the case where x is not equal to, when there is no x dependence. Yes.
right, but that
That's-
means that small doesn't remain small. It's going to oscillate.
Yeah,
Right?
oscillate, but maybe there's not big oscillation. So let's take a look at what you're going to say.
Okay.
But I still don't quite understand it. I haven't really quite understood what you're doing here. So you have a W0, which
It's
is
ansatz, just an ansatz.
No, but what property of W0 do I use? Is that the constant or?
No, W0 will solve the equation.
W0.
L0, W0 is 0.
Okay, that's the first thing. But there are many such solutions, right?
Yes, you have to match it to your problem, of course.
So that will depend on making
Initial data
initial
only.
data first.
Right, so that's not a problem because
So
we
you
know.
just match that with the initial data, then, is that right?
What?
Do I just match that with the
Yes,
do
you.
W0, I just match it with
That's
the
right.
initial data?
Omega 0 will be completely controlled by the initial data.
Okay,
And you know exactly how it behaves, so you don't care about it anymore.
okay, very good.
W1, you choose it to cancel this term by writing it like that. So now,
Okay, so that means I have to solve an inhomogeneous wave equation. Is that correct, more or less?
it's very simple, actually. You see, this is K1 and K2 are quadratic, and this term is also quadratic. So the only thing I'm going to do is I'm going to choose K1 and K2 to cancel out the quadratic term, which is this one. That's all.
Okay, well, I may have to stop you again. 'Cause
Okay, so what does this mean? This means,
But am I right? You're solving an inhomogeneous wave equation in linear order, or?
well, it is at this stage, it is just a purely simple algebraic operation, which I will tell you, okay, I will tell,
No, I'm still confused. The V,
yes,
the V will depend upon you got a V in there, right?
yes.
Now you don't know what V is, so are you plugging V, I mean, are you doing some approximation scheme where you're replacing the V squared by W0 times V1?
No. Here's what I do. I take this expression for W1 as it is, and I apply to it the operator L0, which is derivatives. Now, this K is a quadratic form. So let me write down what do I mean by quadratic form in this case, and then you'll see that what are we doing. It's actually,
I really would like to understand what you're doing.
yes, so yes, you just bear with me because it requires a lot of details. So KUV is a quadratic form of the following type. It is some K hat of Xi over rho and eta over rho and e to the I y Xi plus eta, and then v hat of Xi, v hat of eta, v Xi, v eta, and I need the function k to be a pseudo-differential operator in two variables, which means that this function and all of its, the function k, this is the Fourier transform of k, but the function k and all of its derivatives have to be pseudo-differential operator in the sense that the function and its derivatives are all decaying polynomially. Well, but this is important. This is important to know what is the condition on the k in which we close everything, because this will be the property of your solution. The properties of the solution are derived from the properties of this transformation because this is part of the solution. Now, Now it's very easy. You see, you take this expression and you compute, you put k1 and k2 to be some function k1 and k2. You plug it into this equation.
The dot is the derivative with respect to y or with respect to t? The rho k2 of v dot, v dot.
Yes. No, it does matter. Right? So yes, so the dot is always derivative with respect to rho because it's like t. Yes. Yes. And y is and when there is derivative with respect to y, I will write explicitly derivative with respect to y. So what happens is now you take this kind of expression, you plug it into the equation, and then in Fourier transform space, what happens is that the derivatives, you have to compute this, but derivatives, when you apply derivatives to this kind of expression, you get something nice. You get that the derivative of this is multiplication by xi plus things like that. So it becomes very simple. So what happens is that you get a nice expression from the left-hand side acting on these two expressions, and this term is also a quadratic form with a delta function, if you want, for k hat, right? And so you get an equation which to get the cancellation. And when you write down the equation, I will not write down the equation, but I will tell you what is the result of this algebra, because it is just algebra, okay? And you will see what do we get. Yes. Yes.
I think it's very basic, but it's just I'm missing it. So you're making a change of variables, right? You're making a functional change of variables, which is non-local.
Yes, it's non-local. Yes.
Non-local. But maybe I need a v prime on one of those things to understand what the change of variables is. Right now, I have a v and a v, and I don't understand.
V and v dot.
No, but we still have.
V and v dot. Ah, you ask yourself why I don't have also v prime.
Well, you need a v tilde or something.
You see, there is 1 over rho squared here.
Yeah.
That's a lot of decay.
Yeah, that's fine.
So I move it to the right-hand side. I don't care about it. If I can control the second derivative with respect to y of v. This is part of the problem. This is part of the iteration problem, is to control, let's say in L infinity norm, the second derivative with respect to y of v. If you can do that, then this term is on the other side. I don't care about it.
So in some sense, it's really just an ODE.
Exactly. It's an ODE, and this is exactly the observation that Lindblad and I had. And therefore, whatever the law did with normal form transformations, we did without, because we just controlled the solution in terms of the ODE part, and then we used energy estimates on the v cube term. Now you tell me, how can you integrate this? You cannot integrate it. But in fact, if you do carefully in the small data case, the energy estimate, this gives you a growth of the form rho to the epsilon. And for any epsilon that you want, depending on the size of the initial data. And then, in order to control this term, you can get rid of this term if you can control the equation in a third in the Sobolev norm H3, because you need to control this in L infinity. So in L infinity, to control this, you need at least 2.5 derivatives of v in 1 dimension. So you control it in 3 dimensions by simply taking the 3 derivatives of the equation with respect to y and writing the energy estimate again. And this is actually, and here, it is exactly at this point you can understand why this term is a disaster. Because this term,
Now it comes back into the.
yeah. So now, what happens when you have this kind of a term and you try to do this trick again? What happens is, forget about this term. Let's say that you have these two, and you try to do this trick. So you say, OK, I got rho to the epsilon from the integral. I'm almost there. So all I need is to control 1 more derivative of the equation. So I take 1 more derivative of the equation, and I write the energy estimate again. However, this function, when you take derivative with respect to y, will pull rho out. And that destroys everything. So this is why this problem is fundamentally different from all the previous ones. Now you can say that this is a technical problem with the method that we used. But you will see later that it's not. It's actually a fundamental problem which tells you that the behavior of this equation is fundamentally different from this equation. The behavior of at infinity is very different. OK, so now let me continue by telling. What?
You're making a change of variable here.
Yes. This is a change of variable.
It's not clear to me. Just maybe notationally I'm confused about it. Because
now, just a second. It's not exactly change of variables. But remember,
what is the v? I mean, the v you don't.
v is our unknown.
Okay.
And we want to prove it's bounded. But it satisfies an equation we cannot control. So we make an expansion of it. Omega 0 plus omega 1 plus omega 2 plus leftover.
Okay. So this is ansatz.
Yes. And now the first part.
Not a change of variables.
Yes. And the first part of the ansatz is that omega 1 looks like that.
Okay.
And then we plug it into the equation, and we compute equations for k, which exactly cancels this term.
Ansatz maybe I'm
OK? So now, and the funny thing is that actually it's easy to.
Now you haven't solved for the v.
Yeah, so no, I solve for the k.
So what is v? So,
Any function. Any function. V is the unknown function. But when you plug this in equation and you ask how these two terms cancel this term, you get an equation for the k's. And so I write down the solution for the k.
independent of what v happens to be.
No, v is arbitrary function now.
Okay, that's what I didn't
Yeah.
understand. Because I thought v was the solution to the equation. So that's what got me very confused. So
V is.
it will be easy.
Yes, it will be one day, eventually, yes. So now you get alpha 0 times 1 minus 2 xi eta over p xi eta. And k2 will be 2 alpha 0 over p of xi eta. And the important thing is, of course, what is p xi eta? It's a polynomial. In general, it will be a polynomial. But p xi eta in this particular case is minus 4 xi squared plus 4 eta squared minus 4 xi eta plus 3. And it's elliptic. Okay? So, what? K2 hat.
Okay. So
Elliptic means it always stays away from 0. And therefore, these operators K1 and K2 are nice and smooth, and you can control any number of derivatives of them, and it will just improve. When you take derivatives, everything is nice and smooth as far as these operators are concerned. OK? So that's
you say
one.
I take
So that's the easy part of the problem. Yes. Yes, please.
I plug this in, is that I take W naught plus W1 as you live, right?
Yes.
And then when I apply L0 to that, I will cancel.
I will cancel. You cancel this term only,
Okay.
right? And then in Fourier space, you will get equations for K1 and K2, and you solve them.
You will still have v dot terms, probably. The terms quadratic in v dot, that will not cancel.
Everything cancelled. Quadratic. Everything quadratic cancels.
That's something I don't understand.
So that is only the
OK. That's a calculation. OK? That's a calculation.
Cancel for arbitrary v.
Hmm? Yes, it cancels for arbitrary v. Yes.
So why do you write it as k1 plus k2?
No. Don't you see that there is big difference between K1 and K2? One of them is quadratic in V, the other is quadratic in V dot.
Yes, but if that plays a role, I don't see why the quadratic in v dot terms will cancel.
It cancels exactly. There is, you see,
You need the derivative of y
yeah,
for that, or what?
you don't need derivative. You don't need derivatives in y because the derivative in y is higher order. So I don't care about it.
So
Yeah.
it's the d rho
Yeah.
squared that must come.
Yes. So the d rho squared is important. That's it. And the 1 is important.
So why can I not integrate by
Integral.
Put the dot onto the K2.
What? It's just.
Well, I mean, I should be able to get rid of the dot in the V by some kind of integration by parts.
I don't think so.
Why not?
It's just algebra.
Rho.
No, no, in fact, I don't even know what you mean by V hat of psi, because psi depends on two variables. V depends on two variables. So what are we talking about?
Is the Fourier transform with respect to the spatial level or the time level? Or both?
Exactly.
No, no, no. This is
That I'm confused about.
no. This is the.
These are V-hatted Fourier transform.
You see the. No, the.
I mean,
No.
V is a function of rho and y. So what's V hat of psi? Psi is conjugate to what? To rho or to phi?
Yeah. Well, okay. I wanted to hide it from you, but I can't. So the way you do it is you actually scale with 1 over rho everything. So this is your there is a scaling factor, and then you define the derivative of this. So here. Okay, let me write a little bit more about that. So yes. So I will define the Fourier transform in this way. V of y is 1 over 2 pi, the integral of e to the I rho y xc, v tilde of xc dxc, where well,
Rho times y, I think, wouldn't mean anything.
yes. No, why is it rho? Just a second. V hat of xc. Yeah. Okay. So, no. You scale with rho. So let me explain what do I mean by this. I will define instead of the Fourier transform. Let me define first of all a rescaled Fourier transform. V hat of xc as rho times the integral of e to the minus I rho xc y v of y dy. And then up to a factor of rho, v tilde of xc is the Fourier transform. So the relationship here is that if you use yes, it's yes on rho and psi. Yes, this is also a function of rho, but right, this is also a function of rho, but this is not important here. Okay, what is important is that you want to define Fourier transform with respect to the variable y, and you for each value of rho, and you use rho, large rho as your if you want large rho as your scaling limit. So it is semi-classical in the sense that when rho goes to infinity, it looks like semi-classical. So that's why you put the rho here and you put the rho here. Then if you do that, then the xc over rho becomes xc, and eta over rho becomes eta, and then you will get here rho times y. So then it becomes the same as this one. But I wanted to avoid all this things.
Okay, so let's move on. So
Yeah.
the bottom line is you have some functional of g, which is quadratic.
Yes.
Which is a function of rho and y, so that when I plug it in, I will, at least in leading order, cancel the d squared, no matter
Right.
what b is.
Yeah, you just
Is that
get,
correct?
yes, you just get exact equation that cancel the quadratic term. That's all. So now I don't have a lot of time. So I will tell you now.
So that's just the fact that we will
Yeah. So now I want to tell you what happens next when you try to solve the problem completely.
So this is
Be-
the lower type.
this is Chatin and Delors did this kind.
Not the lower.
Yes. So Chatin didn't do it for this case, but the point is that here the denominator is elliptic, and so the estimates on these operators are very simple. So all the properties, you can take derivatives and everything goes on and everything is nice. So then you ask yourself how to attack.
You can iterate this procedure.
You don't need to, because,
You don't need to?
so I tell you what happens. When you do this, you remove the quadratic terms
Yes.
by this argument, and then you are left with an equation which has cubic term. And the cubic term is now non-local. There is a leftover which is cubic and which is non-local.
So I have the omega 2 that I would have left over.
Yes, there is, there are cubic terms with 1 over rho in front of them, but they are non-local.
Those are not big.
Yes, and they add up to the u cube here, and you would think that also to this one, but in fact it's not. And this is an estimate. So what happens next? Next you say, okay, I know how to remove the quadratic terms. Now I go and try to remove the cubic terms by normal form transformation. And then we find out that in order to remove the cubic terms, we have to do a transformation which is very different now. And this is the new thing, which is done in a completely different way. And now we have to.
Are you making a higher order ansatz, or are you trying to make a higher order ansatz now?
No, I'm trying to remove the cubic terms
Yeah,
now.
so that means you need this ansatz plus.
Yes. So first I do this, I get a new problem. Now I try to solve the new problem by another transformation. So this W is now going to knock off the cubic term, hopefully.
So we've already assumed that the quadratic term has been knocked off.
Yes, right. So now I have something, I want to solve a problem like that. Rho y over rho times u cube. This is the L0. This is the same L0 as before.
Yes.
I want to construct a W that knocks off the leading order.
You have a gamma up there? That's gamma.
Yeah, some function gamma, which is coming from the G over there.
And
Okay.
that function is
Whatever,
bound,
G.
or what properties do you assume about that?
This function is nice and smooth, and if you want decaying, it's decaying faster than anything.
Okay.
The only problem is, you see what is the problem, that if I take its derivatives, I get out factors of rho. That's why it is a disaster.
Okay.
So that's where the problem is. So now you try to solve this by normal form.
That's your G.
Yes. So now you try to solve this by normal form transformation. And we do that, and we write W as a.
Almost start here, is that right? I'll be from
What?
purpose. So we can almost start with this question that you're asking here.
So now I have to solve this, and now I make an ansatz again for W, except that this ansatz is something completely new, and it looks like that. 1 over rho, f1 of rho y, times u cube of rho and y, plus 1 over rho, f2 of rho y times u dot squared u. Yes.
Why can I not view this whole structure as a sort of nonlinear change of field variables with coefficients that may depend on rho and y?
Yes, so you will see what happens to us at least.
I don't understand the general idea yet of this normal form business.
So I
Normal form so far is ansatz.
what?
The ansatz.
No, because you actually find the leading behavior of the solution as a result of the quadratic term, and you pull it out.
Okay.
No,
That's
that means
ansatz.
I solved exactly to leading order the u squared term.
I understand.
And now I try to do the same thing for the u cubed term, and I found out that now I need a different type of normal form transformation which does not have non-local terms, only f1 and f2 which are local. And when you plug this in, yes? Yes. It's long and complicated algebra, but bear with me and you will see what happens. Okay, you plug this in here and you cancel the cubic terms. And then this gives you a system of differential equations for f1 and f2. And you solve these equations for f1 and f2, and you find out that after some change of variables, you get linear combinations of f1 and f2 solve the following equation: f1 double prime equal to minus 3 gamma, and f2 double prime plus 8 f2 equal to minus gamma. This is very simple linear equations.
Gamma is G tilde, or
Yes, this is G tilde. Sorry. So now you see what when I said there are resonances. Because of this 8, plus minus square root of 8 is a resonance. And this means that when you divide, in order to find the f2, and you divide by G tilde, you get that the solution blows up if G tilde has support in frequency around plus minus square root of 8, which means that if you try to construct this kind of solution, it will blow up if G tilde has frequencies near square root of plus minus square root of 8, and from this one it is near 0. So now you see that there are two resonances, which are this one. So the next step is to
Double primes mean what?
two derivatives.
In row?
Yes. Yeah, no, not rho, in this variable. It's a function of one variable. So now let me say in words what happens next. Because you have to localize away from these two frequencies.
Everything is a function of rho y?
Yes, rho y. It's very simple ansatz.
Okay.
Yes, these are coefficients. So now, because you have to localize away from these frequencies, you have to do everything by localizing the frequency of the solution of the whole equation. You localize it on the adic intervals, which exclude these two frequencies, and only on them you use this kind of transformation.
what's the difference between V and U?
Oh, it's the same. It's just you see, this is a dummy variable which is used in order to compute these equations. Yeah, you can. It's the same. It's a dummy variable, right? It's a yes, yeah. It's a dummy variable which you use to find the normal form transformation.
But when you come to sit, you're not after perfect cancellation. You're after things which are good up to.
Yes, up to higher order. Now, so this argument actually has to be extended by putting here diadically a dependence on lambda in frequency space.
Around these two.
Yes, and you stay away from these two. Stay away from it. Then, the next step is to deal with what to do near these frequencies. So near these frequencies, we introduce a new type, still new type of normal form transformation, in which we take these functions to depend also on rho separately, on rho y and rho, okay, separately. And then what happens is that the equations, here the equations are ODEs, but the equation in this case are PDEs, because now it's two variables, and they are hyperbolic. And because they're hyperbolic, the singularity actually propagates. There is still a singularity in the solutions for these functions when they depend on time, and these singularities propagate. So in that case, in order to control the behavior of the functions f1, and in fact, the formula is much longer in this case. There are 4 of them in this case, not 2, which I did not write. There are 4 of them, and you have to solve 4 equations, which are hyperbolic. And when you do that, you have to control the singularity because of the hyperbolic nature. Because what happens is that the singularities propagate. These singularities are frozen in this case, because there is no separate rho dependence. But in the final case, where you look at lambda near these two frequencies, you get hyperbolic problem. The singularities propagate, and therefore you get much weaker estimates. And the estimates that we can get in this case, that's what limits the control of the solution of the problem in the end to only, we can only control the second derivatives of the solution in L2. And this gives us the L infinity. But if we look at the behavior of the solution, you know, when this is omega 1, and we look at omega 2. So we ask the full solution V is omega 0 plus omega 1 plus omega 2 plus good stuff. But the omega 2 shows that there is a singularity which is propagating. And this makes it impossible to extend the result to higher derivatives. So we cannot control higher derivative. And it is all of this is because of this term.
You speculate the higher derivatives actually, grow in time?
Yeah, because
They don't blow up in time.
yeah, not in finite time. Not in finite time. At infinite time they grow.
Yeah, but there's something
Because we
wrong
can
with
see it, we can see it on this term explicitly.
Because of the resonance that you're talking about?
Yeah. Because this W2 solve hyperbolic equations, and these hyperbolic equations just propagate the singularity forever.
How is it now?
Yes.
First you had the W1.
Yes.
You had this ansatz for
Mhm.
W1, they got rid of the V squared.
Right.
Now you have a second ansatz. How is it compatible with the first one? That's what I thought, that this was W2 actually. Okay, now it looks already a little better.
So we have W2. In fact, we have, sorry, W3 plus good. Because I separate the frequencies. I separate the frequencies to resonant and non-resonant. But
contains the resonance stuff or what?
yes, W3 contains the hyperbolic case. So it is actually a much more complicated formula. It has 4 terms. So you have U cube, U dot square U, and then you have U dot, then you have U dot times U squared and things like that. And these functions, there is F1, F2, G1, G2, and they are also all row dependent. So then you get four equations. When you plug it into the equation and you say, let's eliminate the resonance, the cubic resonance, then you get 4 hyperbolic equations, coupled hyperbolic equations. And when you solve them, you get what you get. And that's part of the solution. And this part of the solution is making it impossible to propagate regularity. Okay. So that's what happens.
So the lower solution is going to break down completely the minute you put this G in.
Yes.
And
Yes,
your phases are not going to be well behaved.
No, not anymore, no.
And everything's going to go. All nice estimates will be higher derivatives.
Yes, as t goes to infinity.
Growth on them, but there won't be any.
Yeah, in fact, you can see from the shape of the solution for the resonant term that what happens is that you are actually forming a shock as t goes to infinity. The solution generates a shock as t goes to infinity. It's very different phenomena, and it's very different behavior from what you would expect. And this is small data problem.
Small data problem was just
Right.
almost integrable, except for the fact that you've got this G variable.
That's right.
And the G can be even compactly supported, you say?
Yes, it doesn't enter here, you see, because what you have to solve is this equation, say. This equation, the only thing that matters is, does it have in the spectrum square root of 8, plus, minus, and 0? That's the only thing that matters. If the answer is yes, then you get blow up of the higher derivatives.
So what would you have done if I had added not the minus Laplacian plus 1, but the minus Laplacian minus 1?
It wouldn't work because yeah, so let me say, if you add v of x there, if you add v of x, linear part.
There's another seminar coming
Yeah.
up here in about 5 minutes.
Yes, so let me say very quickly, if you add v of x in general, which is the linear problem that you need, then you have to do everything in terms of the generalized eigenfunctions. You have to do Fourier transforms of these quadratic forms, etc., in terms of the generalized eigenfunctions of the linear problem, which we don't know how to do. Right? If you put there minus 1, then these equations will get messed up, all of them.
Yeah, we're waiting outside, so we should
Okay, we have to stop here anyway.